Okay, we are now going to get started with Chapter 1. Chapter 1 is referring to the air we breathe. The things we're going to talk about here is what is in the air that we breathe. Can it really be hazardous to our health? And how we can understand chemistry to help us make better decisions. In this chapter, we are going to be discussing the contents of the air around us. We will discuss mixtures and the different components of the air. Then we will talk about the pollutants and the air quality. We will then relate this to atoms and molecules and chemical reactions. Let's take a look at these charts. The air that we breathe is not 100% oxygen. If it was, our lungs would start to burn. Instead, it's a mixture of different gases. Actually, if you'll notice here, there's more nitrogen than there is anything else. Nitrogen is an odorless, colorless gas, and it doesn't really react very much in the air. It's 78% of what we breathe, whereas oxygen is only 21% of what we breathe. Oxygen is obviously very important to life, as I'm sure you know. It's what we breathe in and use for biological functions. The other gases that we breathe simply leave as we exhale. So these other gases up here, this 1%, they just go away. So let's take a closer look at what these actual charts mean. We have all these numbers that then add up to 100. These are two representations of the same thing. It's a percentage. Now this percentage could be done by the number of molecules, or it could also be written as the volume. So what that means is for every 100 molecules of air, 78 of them will be nitrogen and 21 of them will be oxygen for the most part. If we're looking at volume, we can look at it in milliliters. And there's 1,000 milliliters in 1 liter. That means for every 1,000 milliliters of air that we breathe in, 780 of them will be nitrogen, 210 milliliters will be oxygen. Okay, so let's look at the components of the air itself and how we actually breathe. Inhale and exhale. So this is what we breathe in, this is what we breathe out. 78% of what we breathe in is nitrogen. Well, that's the same as what's exhaled. That means that our body isn't using this at all. If we look at the argon is a gas that it's kind of like neon, but it's heavier. It doesn't react at all. And so it's called inert because of that. Inert means it doesn't react. So if you're looking at a prescription bottle or Advil or something like that, it'll say inert ingredients. Those are the ingredients that don't react. Alright, so let's take a look now at oxygen and carbon dioxide. We breathe in 21%. We exhale 16%. That's because what's not being breathed by, what we're not exhaling, is actually being used by our bodies. And we look at carbon dioxide. It goes from 0.04 to 4.0. That's a huge difference. Carbon dioxide is a byproduct of many of the biological functions. This whole process is called respiration. Our book defines respiration as the process of metabolizing food to produce carbon dioxide and water. So let's take a look at the concentration. The first one, the percentage, that's parts per 100. That means for every 100%, part of that's going to be out of 100. For instance, 21%. For every 100 molecules, 21 of them will be oxygen. Parts per million is now we're talking about a million. So we're talking about a million here. So if we're looking at ozone being 0.4 parts per million, or ppm, That means for every 1 million molecules, this is scientific notation for 1 million. Notice the 6. That means we move it over 6 spots. 1, 2, 3, 4, 5, 6. For every 1 million molecules, 0.4 of it is going to be ozone. The last one is parts per billion, ppb. So let's take a look at sulfur dioxide. Sulfur dioxide is 30 ppb, which means for every 1 billion is 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. That's why we have that 9 there. For every 1 billion particles, 30 of them are going to be sulfur dioxide molecules. Alright, so let's take a look at some of the pollutants that are in the air. We have carbon monoxide, ozone, sulfur oxides and nitrogen oxides, and particulate matter. Carbon monoxide can make you feel dizzy or nauseous, or give you headaches. Since these are very common symptoms in other issues, it is often mistaken for just simply not feeling well. Many houses now have carbon monoxide detectors because it is impossible to realize that the levels are too high. This is why it's referred to as a silent killer. Ozone. Ozone actually confuses a lot of people because we think of ozone being a good thing, of it protecting us from UV. Well, that's true if it's in the stratosphere. The stratosphere is where the airplanes fly. That is above the area where we breathe. That's above the mountains and all that stuff. So it's very high up there. It's not ground level, what we actually breathe. When it's on the ground level, that's when it starts becoming an issue. Ozone can cause chest pain, coughing, sneezing, and lung congestion. Unfortunately, a lot of the reports out for ground level ozone are very new. For instance, it was only 15 years ago where we had ozone air purifiers, where they were trying to market a way to produce ozone on the ground level to make the air more pure. Unfortunately, that started causing cancer because ozone is actually a carcinogen. Sulfur dioxide, sulfur oxide. So sulfur dioxide, sulfur trioxide. That's why they shorten it to just oxides, because it can be 2 different kinds. They smell really, really bad. You will definitely realize when it's around. In fact, this is what the gas company adds to natural gas for when it comes into your house. Because natural gas doesn't have a smell. So they add sulfur oxides to it to make it have a smell, so that way it can determine if there's a leak. Most of these issues come from burning coal. It's a byproduct of burning coal. Nitrogen oxides, like monoxide or dioxide, is like a really brown, disgusting looking color. And it causes really bad damage to your lungs. It can also react with your lungs, the water in your lungs, to produce some form of an acid. It, unfortunately, is a byproduct of hot engines and power plants, so our cars actually give off nitrogen oxides, which is why we started using catalytic converters to reduce that. And then we have particulate matter. That's actually a very somewhat random one. There's 2 different forms that we are now detecting. PM10 and PM2.5. What this 10 and 2.5 means is how big it is. So it's referring to it in micrometers. So 10 micrometers, 2.5 micrometers. Alright, so we're used to dealing with more English like feet and inches and stuff. So let's put this into terms we can actually understand. This is 0.00004 inches. So that's a really small particle. This is even smaller. The 2.5 is even smaller. 0.0001 inches. So these are extremely small particles. And essentially what we're talking about is somewhat like dust particles, like tiny solid particles or little droplets of water. A lot of these occur naturally, but our activities have been making them worse. So driving cars, burning coal, things like that are making these things worse. So what the government does is they go through a risk assessment where they take scientific data and make predictions so that way we can realize how bad something is for us. They take the toxicity of something, so that's how bad it is to our health, and the exposure, which is how long we're in it. And the more toxic something is, the less you're supposed to be exposed to it. Alright, at the top of this chart you see the word ambient. Ambient means that that's the air that we breathe around us. This chart indicates the amount of pollutant that is acceptable for a time frame. So if we look at carbon monoxide, notice that there's two time frames. There's an 8-hour and a 1-hour. The 1 hour, the concentration is higher than the 8-hour. That's because since you're only in it for 1 hour, you can have a little bit more exposure to it. You have a little bit more time, have a little bit higher concentration. If you're going to be in it for a very long period of time, that concentration has to be really small. There's other ones, such as nitrogen dioxide, which gives you an annual. So for in 1 year, that is the average concentration you'll need. Also notice that these are in parts per million. That means that it's out of 1 million. So for every 1 million particles, only 9 of them can be carbon monoxide. Let's take a closer look at what's happened over the years. On the numbers on the bottom are the years. So it goes from 1980 to 2006. The numbers on the left is the concentrations. And here is the standard. This is what the nation allows. This is what the government allows. So this is how much percentage below what the government allows. Notice that the basic trend is that all of them are decreasing. Also notice that they didn't start detecting the particulate matter until like 1999 or 1990. So that's a fairly recent development. And chances are, as we get better equipment, we're going to have something that's even smaller that we're going to be detecting. The only one that's really above the line is the ground level ozone. And notice it's still decreasing though. It's getting better. Here is a breakdown of different cities. So if we look at the ozone, Chicago actually isn't doing too bad. That's what's closest to us, obviously. We're not that bad. We have some unhealthy days, but it's not horrible. This is a 5-year average. So on average, for 5 years, it's 11 days a year. LA is the absolute worst for ozone. That's because ozone increases with sunlight. So the sunnier something is, the worse the ozone is. So if we look at LA, Houston, Sacramento, things that are really, really sunny tend to be worse. Whereas particulate matter, Pittsburgh is the worst. Once again, LA, and that has to do with the particles that are in the air. So you may have recognized this sheet, or this graph, from either the news or the Weather Channel. This chart was developed by the Environmental Protection Agency to make a clear, concise way of conveying to the pollutant levels to the public. Notice that the top level is green for go, and as you get worse, it becomes more and more red. And this is just a way for them to be able to color code it so it's easy to see and people realize the issues. This is just a snapshot of Phoenix. Notice how it's once again color coded, so we have yellow and orange and green. The green areas are good. So that means that for here they did not really have a problem with carbon monoxide. They really didn't have a problem with particulate matters. But they did have a problem with ozone for a while. Remember, ozone is an issue when it's sunnier. So the sunnier something is, which Phoenix is a pretty sunny city, the worse off it's going to be. This one specifically is orange. Notice it says unhealthy for sensitive groups. That would be like children or elderly or people with health conditions. So here we have a picture of what's called the inversion. When a city is surrounded by mountains, sometimes the cold air can get trapped inside the area. What that also means is that the pollution becomes trapped and the pollution actually becomes worse. Another area where it's an issue is if it's a very polluted area. For instance, Beijing. Beijing is an extremely populated area, and the pollution there has gotten so bad that it's really hard to breathe. Here's a picture of Paris, also an area that's extremely concentrated with people, and the pollution has gotten really bad. Pollution isn't always just caused by people. Sometimes it's caused by natural things. For instance, volcanoes. Volcanoes give off dangerous gases such as sulfur dioxide and carbon dioxide. You see all this steam coming up? That's steam and sulfur dioxide. So remember, the sulfur oxides was one of the pollutants. That's just giving you one example of how these pollutants can cause naturally. So the pollution is caused both by natural and by human activity. That's all we're going to do for this part. The next part of the same chapter, we're going to talk about the chemical processes that are behind this and relate this to chemistry.